Okay, so let's suppose this is a problem, right? The light ray makes this angle 32 degrees, right? And then what they're asking you for is the angle of refraction, right? Okay, so turns out there's no solution to this, but let's just go with this, right? This is not the angle that we use, right? We actually want to use the 58-degree angle here, right? That being 90 minus 32, right? Okay, so let's just set this thing up. This is going to be N1. N1 is 1.33. N2 is 1.00, right? Okay, and then we're just trying to find theta 2. Okay, now we set it up. We go N1 sine theta 1 equals N2 sine theta 2. And N1 is 1.33 sine of 58 equals 1.00 sine of theta 2, right? Gotta put the parentheses there too, right? So theta 2 ends up being the inverse sine of, well, the ratio of these guys, 1.33 over 1.00, right? Sine of 58. Okay, and when you do this, when you evaluate this expression, 1.33 divided by 1 times sine of 58, that expression evaluates to 1.127, right? This thing right here is 1.127. So of course when you take the inverse sine of that, you get domain error because you cannot, there's no point on the unit circle that lies farther from a unit from the origin, right? Okay, so what that means is basically that this thing doesn't escape, that this refracted angle would have to be, what, bigger than 90 degrees. It never escapes. So what happens is it actually reflects. This is total internal reflection. Okay, so what that means is that there's some angle probably less than this 58 degrees, right, that it would actually reflect at. Okay, what's going on here is that the light, you know, if you shine it at this angle, bends like that, right, but at some critical angle like this, right, this refracted angle there is 90 degrees. Okay, so to set it up, you really only just use Snell's law, right? You just go N1 sine theta 1 equals N2 sine theta 2, right? Only what you do is you make theta 2 be 90 degrees, right? So N1 sine theta critical, right, the critical angle, equals N2 sine of 90, right? Well, the sine of 90 is, if we're in degrees, right, is 1, okay, times 1. So basically, okay, so you don't need a new formula. There it is, right? Okay, so the critical angle, technically speaking, is the inverse sine, right? And then we got to figure this out. It's going to be the fast divided by the slow, right? Is that right? No. Yes. Okay, so it's n small divided by n, right? And this is going to be the fast one divided by the slow. Okay? And beyond that critical angle, if you get an angle bigger than that, right? This guy's bigger than the critical angle. What it does is it actually reflects. Okay? So any angle, any theta bigger than or equal to the critical angle, okay, is a reflection. Okay, now remember, it's these glancing blows, right? It's hitting the water at such a, this angle is big, but this one's really small, right? It's the glancing blows that tend to reflect. Okay, and of course this depends on the ratio of these indices of refraction. Okay, so let's figure out the critical angle for an air-water interface, right? This end here is 1.33, right? That's N1 basically, right? N2 is going to be 1.00. We'll just use that, right? So I just go N1 sine theta 1 equals N2 sine theta 2, right? Only we just set this thing up here. N slow is 1.33. Sine of the critical angle, which you're trying to find, is 1.33 sine of 90. Ta-da. Okay. Well, you can see that the critical angle will be sine minus 1 of 1 over 1.33. Whoops. Okay, let's see. This guy is, sorry, 1.00. So 1.00 divided by 1.33. There we go. Sorry about that. So I just go inverse sine of 1 divided by 1.33. I get 48.75 and some change, right, which would round up to 48.8. Okay. You really can't get a wrong answer for this. I mean, the only mistake you might make is put this guy above that guy, but you would get a domain error, so there you have it. Good luck with that, huh?